Okay, it takes a minute, take a couple seconds before the load the screen. We have seen the elements with their dots representing the valence electrons. And those valence electrons, by losing or gaining, forming ions, and they form ionic compound. And ionic compound is the main topic in the last chapter. And we went through naming and so forth. This chapter, we focus on the nonmetals share electrons, share those valence electrons to form bond. And when the valence electrons using dot to show the bonding, that structure we call the Lewis structure. So I'm named after the chemist, American chemist, Lewis. And the Lewis structure shows us how does valence electron form bond. And also you can predict what the shape of the molecule. Today we'll get into shape of the molecule. And then based on shape of the molecule and also the bonding, what kind of atoms in the bond, we can predict what are the physical chemical properties, how they behave. Are they soluble in water, for example? And can they stick to the glass, for example? We can all predict based on the shape of the molecule. And so that's the main part in today's lecture. Please feel free, raise your hand. You know, raise your hand is under the participants. So raise your hand when you need to be slowed down or, okay. And so the two nonmetals, when they share valence electrons, because they all try to gain electron and become a noble gas, which is eight electron configuration. The nonmetal tend to gain electrons, but if both of them try to gain and when they form the bond together, they will have to share. So for example, we have the two examples. One is F2. F2 is fluorine in the element form. It has two fluorine in one molecule. And I will show you how does the F2 form bonding. I don't have a tablet yet, so the fluorine, it looks like that. It has 7 valence electrons. So I'll show you 7 dots. The other fluorine also have 7. So when this fluorine form bond with the other first fluorine, they will have to share the electrons. So let's say I use a slightly different symbol for those electrons. I use a cross. So the second fluorine has all the cross electrons, and the first one has dot electrons. And how they can both become noble gas, become 8, is they share this one pair of electrons. Shares one pair. And after sharing the one pair, and you can see this fluorine have 1, 2, 3, 4, 5, 6, 7, 8 electrons. And this fluorine also have 8 electrons. And by sharing, they both become 8, become noble gas, and then stable. So the analogy for this will be the 2-person. They share in one house, and there's only one bathroom, one kitchen, one fridge. And if, imagine one person has access only to the fridge and no kitchen, and the other person have access only to the kitchen, no fridge, and then they are not happy, neither will be happy. But by sharing, if they share the kitchen and share the fridge, then they both become satisfied. So it is similar to this kind of situation for the fluorine share electrons. And the water is very similar. Water, it is compound. It has 2 elements. And the water, when they form bond, you have oxygen in the middle and have 6 electrons, because oxygen is group 6, have only 6 electrons. Oh, there's some, come on. I cannot really change the mode for my pen. Interesting. Anyway, these two dots. That's why we need a tablet. This pen, okay, finally. All right, so now it's better. Okay, I got stuck in the eraser mode. I cannot get back to them. Okay. Yes, one of you raise hand. Stephen, yes? You have suggestions? Hello, Stephen? Can you hear me? Hello?
He left a comment in the chat. He said, is that fluorine sharing 2 electrons?
The chlorine, yes, chlorine will be similar. Chlorine will be similar to fluorine, share 2 electrons. The Cl2. And the same with the
No, he's asking
Br2, bromine, and so forth. That'll be similar. I'm struggling to get back to no eraser. Okay. Did not responding. Oh, there we go. Gosh. Okay. So how does the water form bond? Let's continue with this. The 2 hydrogens. Okay. This cross electron belongs to hydrogen. And we have another hydrogen here. And this electron belongs to the hydrogen. So when the water form bonding, the oxygen have 6 valence electron is not stable because it's not 8. And how the oxygen become 8? They share 2 electrons, 1 from each hydrogen. So this hydrogen share its electrons here. And the other hydrogen share another one. So together, oxygen will have 8. And the hydrogen, it have 2. Because the hydrogen has only 1 s electron. To become the nearest noble gas, it has to be the helium. And the helium is noble gas. So hydrogen share 1 become helium, become stable. And same with the other hydrogen. So that is how does the water form bond. Okay, any questions? So this is, you can see, between 2 atoms share only 1 pair of electrons. 1 pair electron, that will make it a single bond. We call it single bond. 1 pair electron is single bond. Okay. And between 2 atoms, they can share 2 pairs of electrons. More than just 1 pair. Okay. Okay, give me a second. Okay, let's continue on this. Between the 2 atoms, they can share 2 pairs of electrons, which means 4 electrons. And that happens, for example, the O2. If you remember, the have no fear of ice cold beer, the no oxygen is the oxygen's 2 atoms form a molecule as an element. And how they form. They form the bond is between 2 oxygen atoms. The 2 oxygen, each one have 6 electrons. So this is 1 oxygen. I move the 2 valence electron on one side of the oxygen. It actually, there are up to 8 valence electrons on 1 atom. You can put those electrons any place as you wish. So I put 2 oxygen, 2 electrons here. The other oxygen also have 6 electrons. And the other oxygen also put these 2 in between the 2 oxygen. So when you have this kind of layout, and you can see for this oxygen, there are 1, 2, 3, 4, plus 4 more. That's 8 electrons. And for the other oxygen, very similar. This oxygen also have 8 electrons. So by sharing 2 pairs, sharing 4 electrons, each one achieved octet, like noble gas. And O2, it has 2 pairs of electrons. We call it double bond. So that's where double bond comes from. Double bond means share 2 pairs of electrons. Okay, any questions?
Yes. I do
Yeah.
have a question. What does it mean to be a shorter and stronger than a single bond? Like,
Oh,
what
very
do you
good question. Yes, I was about to skip this because I cannot really go through all the. So electrons have negative charge, and both oxygen, the nucleus, have positive charge. Okay, there are 8 positive, 8 protons in each nucleus. So those electrons right in between, they will be attracted by the nucleus, the protons. The more electrons in between, then these 2 nucleus will be brought closer together to each other. The more electrons share in between, the nucleus will be closer, which means the molecule will be smaller, more compacted. And since they are closer, the electron will have lower energy, which means a stronger bond. So keeping it short, the more electron in between, then the bonding is stronger. How to make them stronger is bring the 2 nucleus closer, a smaller molecule. So that's what the stronger bond means. It's a shorter bond length. The bond distance between 2 nucleus will be shorter, just because there are more electrons in between. The electrons kind of like a glue. Okay, the more glue between nucleus, you have stronger bonding. Stronger bonding, just like 2 items. Yes, some of you ask questions.
Yes, but these are still considered as a nonpolar covalent bonds because they're sharing equally the electrons,
Correct.
right?
Yes. The polarity I need to bring up the next time. I think the next lecture period I'll probably get into the polarity. But yes, you read ahead in the chapter. That is these 2 both are oxygen, so the electrons, these 2 pairs equally shared, and that make a nonpolar bond between the what we call pure covalent bonding between 2 oxygen atoms. Yeah, very good question. Yes. One more question. Yeah.
Does the orientation of the electrons matter in this Lewis structure?
In the Lewis structure, it does not matter much. As long as if there are electrons in between the 2 symbols, 2 atoms, those electrons should be the bonding electron, or we call them bonding electron. And the electrons not between, like those electrons, we don't call them bonding electrons. We call them lone pairs, which means not being shared. Okay. Those electrons not being shared, we call them lone pair, like a lone, loner by themselves. Those electrons not being shared.
Oh, I see.
Yeah, so these are non-bonding electrons, Yeah, sorry, my highlighter, I'm afraid of playing with my highlighter back and forth. Sometimes don't work. I stick with my pen, so. Yes, any questions? Any more questions? Yeah.
Thank you.
Okay, you're welcome. So you can see the between 2 atoms, they can share 2 pairs, and that make a double bond. They can even share more. Between 2 atoms, they can share maximum 6 electrons, and that'll be next one. We call it triple bond. The triple bond. So the example for triple bond, there are many molecules can have a triple bond, but the simplest will be the nitrogen molecule. Nitrogen molecule is a two, both are nitrogen. And if you check your periodic table, nitrogen is group 5. Group 5 have 5 valence electrons. So each nitrogen have a 2 plus 3 more. How each nitrogen become 8 is they share, each atom shares their 3 electrons. So when you get together, for this nitrogen, it has 8. 2, these are non-bonding pairs or lone pairs. And then we have 3 pairs that are shared. You can treat like these 3 belong to the left-hand nitrogen, and these 3 belong to the right-hand nitrogen. But after share, they both become 8. And this is a triple bond. Triple bond is a share 6 electrons, so that makes it even stronger bond, and the distance between 2 nucleus is even smaller because they share even more electrons. But how exactly they share 6 electrons? The Chem 1A, next method, general chemistry, you will learn how actually they share those 6 electrons. Any questions? Okay. That's basically when you have triple bond. The triple bond, there's an easy way to show those. We simply use 3 lines between 2 nitrogen. 3 lines. Each one line means 1 bond, and then 1 line means 1 pair of electrons. So this one line, it roughly corresponds to this pair of electrons. And here another pair of electrons, here another pair of electrons. So there are 3 pair of electrons. That's where the 3 lines come from. Okay. Okay, Abram, your questions?
No, that was a while ago.
Okay, I need to lower your hand. That way, oh.
And I did ask my question.
Okay, yeah. Yeah, straight. Yeah. And this is how we form triple bond. Okay, let's see. Oops. Here's a little practice. Just kind of practice. Can we realize which atom is octet? And keep in mind, hydrogen is a very important exception. Hydrogen only needs up to 2 electrons. If hydrogen share 1 and become 2, and that become helium, it is also a stable, even though it's not technically a 8. Because octet means most nonmetals should achieve 8, become stable. So keep in mind this, and then we can look at these 2 examples, these 2 Lewis structures. So if you look at the first one to the left, and then we look at one by one. Fluorine, you can see there are 8, so that's octet. This chlorine, if you look, this carbon, look around, we have these 2, there are 2 more, there are 4 more. So that's also 8. And this carbon will be the octet. And the same thing for this carbon. It's also octet because you have a 4 electron here and 4 more, so it's like 8. And then we look at the hydrogen. The hydrogen, that's 2. That'll make it like helium, which is octet. Even though it's technically not 8, but we consider stable because hydrogen can only achieve like the nearest noble gas, which is helium. So this full structure, every atom is octet. Okay, no problem. And you look at the right-hand structure. Fluorine is octet. And then look at this carbon. Is this carbon octet?
No.
Yeah, you can see there's only
6
1 pair and 6 electrons. So this is not octet. This is not octet. but all the other atoms, you see this carbon is octet, the hydrogen is 2, this hydrogen 2. So everyone else, all the other atoms are octet except this carbon. And so this carbon, it violates, it did not fulfill the octet. And that's basically the answer. Take a little practice, get used to the how to count valence electron around each atom. Because later, when you draw the Lewis structure yourself, you need to constantly check if your structure it fulfill octet rule. So take some practice, get used to this. Okay, any questions? The bonding patterns, before we get to that, okay, it shows my internet is not stable. You guys okay? My internet seems like there's little message for my, okay. We have, for the valence electron in the Lewis structure, we have 2 kinds. Just make it easy to communicate, to discuss. One is bonding electrons. Bonding electrons are the electrons shared, exist between 2 atoms in the Lewis structure. And the lone pairs are the electrons not being shared. Okay, not being shared. And so here's the carbon dioxide Lewis structure. And you can see the question asks about how many bonding pairs and how many lone pairs. And let's just first categorize. I will try to use a triangle for the bonding pairs. Okay, triangle for bonding pairs. The bonding electrons between 2 atoms or 2 symbols in the Lewis structure. So you can see these 4 electrons are the bonding electrons. And same with this, bonding electrons. So that means all the other electrons, there's 1 pair here, 1 more pair here, 1 more. So 4 more pairs, those are not bonding pairs. So we call them lone pairs. So the lone pairs, circle, circle. And once you know which one's bonding, which one's lone pairs, and the question, easy answer. The question asks, how many bonding pairs? Bonding pairs, these are triangles, the ones between 2 elements. And we have 4 here, so 8 electrons. And that's 8 electrons, which means 4 pairs. The answer will be 4 pairs, 4 bonding pairs in the carbon dioxide molecule. And the lone pairs are the electrons in the circles. Those are not being shared. So we have 4 lone pairs. So keep in mind, there are many hundreds of molecules we can work on in the Chem 2A level. And the number of bonding pairs, lone pairs, can be in the full spectrum. And this, in the CO2, in the carbon dioxide molecule, it happens to have the same number of bonding pairs and lone pairs. But this is not the general situation for all the molecules. So recognize what is a bonding pair, what is a lone pairs. The bonding pairs, oftentimes they use a line. So this Lewis structure, we can write down like this. Just use 2 lines. Oops. Okay. I have some tiny dot shows electrons. Anyway, I tried to erase, but I'm afraid of using this. It did not really work out very well. So, okay, I just gave up. This part is not supposed to be the linked together, but this is the carbon dioxide if you use lines instead of 1 pair. 1 line represents 1 pair. So that'll be the bonding pairs, lone pairs in the Lewis structure. Okay, any questions? All right, so move on to next. Polyatomic ions, we learned about the Nick, the Camel, Clan, Super, Phoenix, and so forth. And for those polyatomic ions, you probably notice they are made of nonmetals. One nonmetal bound with oxygen. And so how is the bonding within the polyatomic ion? They're all sharing electrons, the covalent bond. And that is the bonding between the two nonmetals in the ion. And so, okay. And you can see the, this is the structure for nitrate. Nitrogen in the middle, oxygen is the red color. And between the nitrogen and oxygen, it is sharing electrons. It's covalent bond. And likewise for ammonium ion, NH4+, that is also the covalent bonding between the nitrogen and the hydrogen. And also for sulfate. Sulfate is also sulfur oxygen share electrons. But between the ions, that is ionic bonding. So this dot representing the ionic, which means the opposite charge, attraction, attract to each other. So that's the, between the ions, that is ionic. Within the polyatomic ions, within the ions, nonmetal with oxygen or any other elements will be the covalent bonding. So the covalent bonding is very common, and it's very strong, very stable. And this is sulfate ion, and later we'll learn about the shape. The shape of the molecule or ions can be easily predicted by the Lewis structure. The bonding patterns, this is the bonding patterns. I can go through all of these, but we have a simple rule to summarize. Still, the carbon has 4 valence electrons, and to become 8, need to share 4 more electrons from the other atoms. And the way to share 4 more, there are different possibilities. It can be 4 single bond or 2 double bond, because each double bond is 4 electrons. And since you have 2 double bond, that'll make it 8. It can be a single with a triple. So single is 1 bond and triple is 3 pairs. So that'll make it 4 pairs. Also make it 8. It can be also the 2 single or 1 double. So 2 single and 2 pairs on the double bond. So together give you 4 pairs, 8 electrons. So these are more possibilities. The life on the Earth is based on the carbon bond. One main reason because carbon is very versatile. It is capable of forming all different kind of sharing electron covalent bonding, and the structure more flexible, can be easily changed through the chemical reaction into the single or double or triple bond. So because carbon is has a bigger versatility. The nitrogen have 5 valence electrons. So share 3. Share 3, that becomes 8. And it can form the 3 single bond or 1 triple or 1 double, 1 single. So these are more possibilities. Nitrogen in the end normally will have 1 lone pair in the structure. Okay, 1 lone pair, not being shared. Oxygen 6 electrons, so need to share 2 more. And oxygen form bonding typically have 2 bonds, can form 2 bonds. It can be double or 2 single bond. And the oxygen, after forming sharing electrons, they have 2 pairs of electrons unshared, so there will be 2 lone pairs. And hydrogen, halogen, the group 7 elements, they have 7 electrons, share 1 more. Hydrogen share 1 more, become helium. So all these atoms, they form 1 bond. For the fluorine, chlorine, bromine, they become 8. Hydrogen become helium, become 2. So they have different ways, but they all become stable after form bond. The beryllium boron is listed here. For our class, you don't need to deal with the beryllium and the boron because they are exceptions. They are not following octet rule. So I'll leave it just like this. I will not ask any questions. In Chem 1A, you will find some bonding, some molecules, and their shape. It is actually depends on boron, and that is not octet. And there are many other situations that is not octet when you study the Chem 1A. So the bonding pattern looks kind of difficult to grasp in the short amount of time. Let's move on to the next one. There's a simple way to memorize this. I call it the HONC rule. The HONC rule sounds like a when you push the button you're driving and push the button in front of you, the honk. It sounds like a honk. The HONC rule means for these 4 elements, hydrogen, oxygen, nitrogen, carbon, the number of bonds, it is 1, 2, 3, 4. So the HONC, it actually represents the simple way to memorize how many bonds each of these 4 elements normally form. And if for Chem 2A class, this is the most important for writing Lewis structures, because this can help us easily decide which one can be the center of the molecule or which one cannot be the center of the molecule. Follow simple HONC rule. There's only 4 nonmetal here, and except hydrogen, these 3 are in the second row in the periodic table. What about the other nonmetals? The other nonmetals, because the periodicity, the elements right under those elements, under those 3, they share essentially the same bonding pattern with some exceptions. So that's what we call it extended, because not only these 4 elements, the other elements have the similar bonding pattern. Like I mentioned before in the last slide, hydrogen and halides, they tend to form only 1 bond. Okay. I leave a question mark because there's many exceptions for these elements that has question marks. They may not follow the HONC rule listed here. And so, but the fluorine is always 1 bond. Chlorine depends. Chlorine most often is a 1 bond, but can be more. And when you study the Chem 1A, and even later in this chapter, you will see some exceptions. But again, for Chem 2A, we stay with the HONC rule. Okay, we don't go beyond HONC rule. Make sure you master how to use HONC rule to draw Lewis structures. That's the most important. Okay, you guys okay? Make sure I make sure you guys are all with me. You can unmute yourself. Hello?
Yes.
Okay.
Yes.
Yeah.
All right. Any questions? It may still sounds confusing because I've been scribbling all over the place. And so let me kind of go over the oxygen group 6. So in the same group, sulfur, selenium, they follow mostly the same bonding pattern. But with sulfur, selenium, there are some exceptions. Keep in mind in our class, you can forget about the question mark when you consider which atom be the center or not be the center. We'll get to some examples how to use those. Oxygen form 2 bonds, nitrogen 3 bonds, and same in the same family, in the same column, phosphorus, arsenic, very similar. And last, the carbon 4 bond, silicon in the same family tend to form 4 bonds in the compound. So that's what we call the HONC rule. HONC rule is when you draw the Lewis structure that help you decide which atom is most likely to be the center. The atom that can form more than 1 bond is more likely to be the center. And the atom can form only 1 bond can never be the center. So for example, the hydrogen and fluorine, they can never be the center. And the carbon is the most likely in the center, and so forth. And so we'll get into next show you how to draw Lewis structures, and we'll use the HONC rule. So to draw the Lewis structures, some of you might have learned the Lewis structure in high school, AP class, and so forth. You might learn about Lewis structures. Actually, draw the Lewis structures is better follow those 4 steps. I will go over those 4 steps, but then later use example to explain how to use those steps. The step number 1, it is we sum up all the valence electrons in the formula. If you are given a molecular formula, you know how many of each atoms, add all the valence electrons together. If one element has more than 1 atom, you times the number of atoms in the formula. And how do we find the valence electrons? As you remember, the number of valence electrons, it is the group number. So for example, hydrogen's group 7, each one have 7 valence electrons. Oxygen, sulfur in group 6, so each one has 6 electrons. And carbon's group 4, carbon will have 4 electrons in the valence electron. And then before we draw the Lewis structures, we arrange the atoms and link with single bond. Single bond. It is a single bond first. Later, we might need a double bond or triple bond, but in the beginning, let's draw only single bond. And then when you lay out atoms, well, if you have a formula, then you need to decide which atom be the center. Which atom cannot be center? How do we know? We use the HONC rule. The HONC rule says the atom most likely to be the center are they more to the right. Carbon is most likely. Next one, nitrogen. Hydrogen never be the center. So when you lay out atoms, make sure you use the HONC rule as a guideline, as a guide. Carbon most likely be the center, and then nitrogen, and then oxygen. Always put a hydrogen, fluorine, because fluorine, chlorine always can only have a chlorine. This is not a very good writing for chlorine. Chlorine always be the center, be off the center. Very rare be the center. There are some examples chlorine is the center, but in our class, we'll try to put a chlorine as the outside atoms. And so that's the rule how you lay out the atoms. And the next, since we count all the valence electrons in the first step, and then we link single bond, each single bond is 2 electrons. Each single bond I want have only 2 electrons. So there are a number of electrons remaining, and those remaining electrons should all show up in the Lewis structure. And that's why we do the step 3. We basically use all the remaining valence electrons to populate, to spread around those atoms. And make sure I have all the valence electrons show up in my Lewis structure. That's very important. You show all the valence electrons. And where do we start? Start with terminal. The terminal, it also means outside. Okay, it's not a very good handwriting with mouse, but terminal means the atoms outside, not as central. The counterpart for terminal will be the central. Central atom, terminal atom. And I think the terminal atom kind of relate to the, those who've been to some big airport like LAX. LAX, the whole airport have, each airliner has its own hub. And each hub have several terminals. Each terminal will link to, will direct the passengers to the specific airlines they're going to go fly with. So the terminal, it is kind of come from that idea. It's basically the very end of one structure. Terminal and hub is just a counterpart. After we make the terminal atoms octet, then if there are any remaining electrons, valence electrons, then finally put on central atom. And finally, we build a double or single bond. So step 4, we need to check, make sure all the atoms, if they are octet. If the central atom is not octet, then we share electrons to form the multiple bond, double or triple bond. So basically, that's what sounds like very dry. Let's move on to examples. You know, I like examples, so let's go through some examples. Let's say we're going to draw a Lewis structure for carbon dioxide, and let's follow those steps. Step 1, count all the valence electrons. When you count the electrons, carbon has 4 of each, and oxygen have 6 each, but there are 2 oxygens, so 6 times 2 and plus 4 add together, and that's where it gives us 16 electrons. So let's count the valence electron first, and then next follow steps. Then we lay out atoms and link with single bond first, and we use HONC rule as a guideline. The carbon oxygen, which atom is most likely to be the center? The HONC rule says number of bonding is 1, 2, and 3, and 4. Carbon can form 4 bonds. It's most likely to be the center. Oxygen is more to the left, so carbon should be the center. We can first lay out like this, and then we think about where should I put the oxygen? Should I put the oxygen here? Well, if you put oxygen here, then the oxygen becomes center. That will break the HONC rule. So the other oxygen better put it here. So that's why we use HONC rule to decide carbon be the center. And then step 2, we link with single bond first. So that's basically step 2 looks like. After doing this, you can see we have 2 single bonds been laying down. Each single bond have 2 electrons. Okay, this is 1 pair electrons, here another 1 pair electrons, so that's 4 electrons. And the total 16 subtracts these 4, we get a 12. It's very important. We need to keep track how many electrons left. Okay, now we have basically 4 electrons down, 12 to go. And then we move on to step 3. Step 3, oh, sorry, my PowerPoint already have those. I forgot I have those. It's actually a lot of fun to draw those. I try to, in the future, not use animation. So, but anyway, that's what it looks like. And next. Step 3, attach atoms with pair of electrons. The remaining valence electrons. We have 12 left. And start with terminal, meaning the oxygen first. Okay, we start with the oxygen first, make them octet. I already have animation. This is what it looks like. Okay, so remember this is 2 electrons here, not 2 electrons, and besides these 4, we have 12 electrons. Those 12 electrons will put on the terminal. The oxygen make them octet first. So with 12 electrons, I put 6 more here. Make this oxygen octet. And keep in mind, we have 6 more. And the other 6 goes with the other oxygen. So once this is done, I used up all the valence electrons. And to be sure, let's do a head count. Do how many electrons I have used. If you can check, this oxygen have 6 plus 2 more, that's 8. And the other oxygen, same thing, because they are exactly the same bonding situation. You have 6 here and 1 bond, that's also 8. Both are 8, add together gives 16. So I don't have any electrons left. This carbon have no electrons to stay, because I ran out of electrons. Well, You can see the carbon is not octet. Carbon is not octet. How to make the carbon octet? Now this time we share those lone pairs. We share lone pairs instead of stay with oxygen only. Let's share this pair between the carbon and oxygen. Becomes this. This pair is just shared. It is basically was here, and now shared with carbon. And then now you look, this oxygen no change because oxygen still have an 8. Oxygen after shared this one pair did not affect the octet, so the oxygen no change. But the carbon now you have 6, and it actually become better. Okay, but still carbon is not octet. How to make this carbon octet is finally this oxygen share this pair, and finally become this. And once it reaches this point, all the atoms are octet. And so that's how we build the Lewis structure. It sounds like complicated, but the key point is first make sure remember the HONC rule, because the HONC rule it help you decide which atom be the center. And next, keep track on the valence electrons. Okay, keep track. That's why we do the step 1 counting electrons. And follow those 4 steps. It takes some practice, but you will get it pretty quick. The Lewis structure, the good part is the whole chapter, no need of calculator. It is more visual. And remember, very common patterns. It's very easy to apply. Okay, so any questions about how to draw Lewis structures for carbon dioxide? Yes, okay, Prince?
So when drawing out the Lewis structures, we have to make sure all the elements are in an octet, correct?
So keep in mind that hydrogen is the only exception.
Right.
Hydrogen need only 2. All the others correct. Has to be 8.
Okay.
Yeah.
All right. Thank you.
Very good. Yeah. Good question. Okay. Yes, Abraham. Yes, you can unmute yourself. You can unmute yourself.
Yeah. Okay. So for the very last step, doesn't that mean the carbon has 8 electrons?
Correct. Correct. If you look at the carbon, there's a 1 bond, 2 bond, altogether 4 bond. It is basically 2 double bond, which is a 4 bond. 4 bond, each bond is a 1 pair. So there are 4 pairs, and that's 8. So this carbon is also octet.
Okay, but doesn't the carbon has 4 electrons, valence electrons?
Correct, yeah. Carbon had 4 to begin with, but since it received the share from oxygen, basically oxygen share, each oxygen share 2. Okay, so both oxygen share 4. That's how the carbon finally kind of gained 4. It's actually not gained 4, but have the 4 more to share with and to reach octet. Kind of makes sense?
Yeah, yeah, kind of.
Yeah.
Thank you.
Yeah, so basically you can treat it like this, like the kind of, oops, carbon, okay, let's say I have 4. Okay, this is carbon 4. And oxygen have 6. And oxygen share 2 with this carbon. Okay. That way, this oxygen will be octet. And this carbon now you have 6, right? Have 6 electrons. Well, that's why we need another oxygen. This oxygen share 2 also, just like the other oxygen. And you can see this oxygen, after sharing, it reaches the octet because it get a share 2 electron for carbon. And after this, you can see this carbon, you get 8. Because there are 4 to the left, 4 to the right, it also becomes 8. It reaches octet. Okay, makes sense?
Yes. So the target is to complete the outer shell.
Correct. The valence electron, it is outermost shell, and the outermost shell all the atoms become noble gas by sharing electrons. Yeah, by sharing electrons. Okay. So that's how the molecules form bond. The carbon dioxide, it is a very common molecule, but it's kind of intimidating example to show. It kind of looks messy. It forms double bond and so forth. Keep in mind, I use water in the beginning of the lecture, and water forms single bond only. And then O2, the oxygen molecule O2, it has one double bond. And so the real world bonding, it is a mix. It has both a single and double, and some even have triple. So we'll see some more examples of how we apply. But keep in mind these 4 steps. That is try to be helpful for you to build the Lewis structures. Follow HONC rule first and single bond first. Okay, that will help you very easy to reach to the correct Lewis structure. If you follow the HONC rule, the more to the right, more in the center of the molecule. And so let's see the next example. Okay, let's say we have a NOCl molecule, draw the Lewis structure. So after use, make the terminal outside atom octet. I have 2 electrons left. Those 2 electrons I can leave on the central atoms. Very, very important, on the terminal first. Okay, this is a typo. I do have 1 pair on nitrogen. Okay. To be sure, let's do the head count again. This fluorine have 8. And this oxygen have 8. Okay, remember, we already count those bonding electrons. So 8 to 8, that's 16. 2 more on nitrogen, so that's 18. At this point, we used up all 18 electrons that we start with. And we notice both fluorine and oxygen are octet. And is nitrogen octet? Okay, is nitrogen octet at this point?
No.
No.
Yeah, because there's a 1 pair, 2 pair, 3 pair, only 6 electrons. The nitrogen is not octet. How we can make a nitrogen octet? It is for those terminal atoms share their lone pair electrons. Share the lone pair electrons. Okay. Now, actually, I just show you the how the final decision is. But keep in mind, we have fluorine and oxygen both can share. We have to think about fluorine, oxygen, which one should share? Which one can form more bond? Can fluorine form 2 bond, or can oxygen form 2 bond?
Oxygen.
Yeah, because fluorine can only form 1 bond. It has 7 valence, only 1 bond. So fluorine cannot share this bond. It won't have a share. It's oxygen share. So finally, oxygen share 1 of its 6 lone pair electrons. So this electron comes from the oxygen. And that's in the end, the bonding should look like. The nitrogen and oxygen should have a double bond, and the fluorine and nitrogen have remained a single bond. And so that's the final Lewis structure looks like. So keep in mind, in the end, we have to remember the HONC rule, the extended HONC rule. When you have both atoms can share electrons, which atom should be able to share without breaking the HONC rule? Only with oxygen, you share the lone pair, form double bond. It's more legit. Fluorine cannot form because fluorine is after shared bond, it will break the HONC rule if it forms double bond. And also, if fluorine share electrons, oxygen will end up only one bond, and that you break the HONC rule twice. So that's how we draw the Lewis structure if you start from formula. The HONC rule stay all the time. And so this is another example to show the Lewis structure. Stay with the HONC rule and the counting electrons. And you can see I was in a rush. This is PowerPoint. I rushed, and there's some editing, and I did not save the change, I think. Not change. So there's some problems with find the Lewis structure. It is when you have a double bond with oxygen and a single bond with fluorine. Any questions? Okay.
So does it have a single bond or a double bond now? Like
which one? Which one?
The whole molecule.
The whole molecule. The whole molecule, you can see there's a one single bond between fluorine and nitrogen, and there's a double bond between nitrogen and oxygen.
Okay.
Yeah, and all the atoms are octet because this fluorine have 8, this oxygen is 8, and nitrogen have one single bond and a one double bond. So that's add together as a 3 bond plus one lone pair. That'll make 8 electrons. So all the atoms fulfill the octet rule after forming the one single bond and one double bond. Okay, any questions? Okay, I think this Friday we will have a lab. The lab will be very short, and we might be able to get more practice on this. And also the week after, I believe the next week or week after, we will have a practice on the Lewis structures. So by the time we all can get together and discuss and walk you through this again. We do have an online assignment, on the draw Lewis structure on this whole chapter. So yes, there are some of you ask questions. Yeah, unmute yourself. You can mute.
For the lab, do we get on Zoom like we would usually for our lectures, or is there going to be a link specifically for a website we need to go to?
The lab depends. For this week, we have a density lab. That is, I'll give you a handout. Is on Canvas. You download and work on that. And the simulation is online. So you download that, print it out, and fill the form with the handout. So Friday, I will give you that PDF file today, and you can work on that early. You don't have to wait until Friday to work on that. And the following 2 weeks before spring break is all dry lab. It's just naming and the Lewis structure. So that's yeah. Anyway,
So you still meet at a Zoom conference or?
Friday, yes. I made an appointment. It's on the Canvas. So that is if you have any problems with lab, we can go through Zoom conference. But that is not a lecture. It is an appointment. It is kind of like an office hour. But keep in mind, the Friday morning, afternoon are the lab hour. So we are supposed to be get together. So make sure attend the morning, afternoon session. But I will try to make it it'll become a more smaller group, and that'll make it easier to conversation style. Friday is more conversation style, but it's still through Zoom. Yeah, and okay, let's see some more. Oh, this structure, I must use a different PowerPoint. This molecule, I already showed all the steps. Okay, so before I show you the PowerPoint, think about this. C₂HCl, which atom can be the center before we counting electrons?
Carbon.
Carbon can form 4 bonds. Hydrogen 1 bond, chlorine 1 bond. So carbon can form 4. Carbon has to be the center. And that's why we have this layout to begin with. The hydrogen cannot put in here because chlorine can only form 1 bond. So hydrogen cannot go here. So that basically determined this is only one possibility. And either chlorine cannot go here either. And that'd be a problem because the hydrogen will become a 2 bond. So that's why the carbon has to be stay in the middle and 2 carbon together. Hydrogen, chlorine, 1 on each side. Okay. And the next we count electrons and single bond first. And then we put the electrons on the terminal atom first. Hydrogen only needed 1 pair, 1 electron, so stay. No more long pair on hydrogen. Chlorine need 8, so that'll make it octet. And after we put the electron on the chlorine, we can do a count. Okay, let's practice on the counting. How many electrons in this structure so far? This chlorine have 8, and so 10. Just add together, 8 plus 2, 10. And 10 plus 2 give you 12. We start with 16 electrons. Now there's 12 electrons in the structure. I have 4 more. 4 more electrons. We can next move to the central carbon, make them octet. So we can make the carbon, use all 4 electrons on this carbon, make it happy, make it octet. Well, after this, you notice we run out of electrons, no more electrons. But this carbon is not octet, have only 4 electrons. How to make this carbon octet? It is this carbon share both pairs, and that end up a triple bond between 2 carbon. And after this, each atom become octet. The both carbon now each one have 4 bonds, so both become octet, and that is the end for this Lewis structure. And so this is a third example, kind of run faster, but as you see more example and do more practice, make sure follow those 4 steps and building structures. The exceptions, again, our lecture, our Chem 2A, we don't deal with exceptions, but keep in mind there are exceptions for some elements. Beryllium, boron, these are tend to be below 8. And there's some elements, sulfur, phosphorus, and even bigger atoms can be more than 8. So, but that's beyond our Chem 2A scope. So don't worry about those beyond octet. Okay, so that's about the octet rule and the exceptions, but focus on the 4 steps when we draw Lewis structures. A big part for the this chapter exercise and online quiz, it is about familiar with how to construct Lewis structure for a given molecule.